Hey guys, this is Barry. I'm going to compress the information in Chapter 1 down into this mini lesson for you. First two items on the docket, analog versus digital. Analog data, anything that can be measured and is represented by a continuous series of values. Digital data is anything that can be counted, and these are represented as discrete values. Examples of analog data: your height, some distance, where precision can only be approximated. Examples of digital data: how many jelly beans are in this jar, and number of students in this class. The fundamental analog wave is a sine wave, nice smooth curve. The fundamental digital wave is a square wave. Next topic. Just what is a computer system anyway? A computer is a multi-purpose device that accepts input, manipulates or processes data, produces output, all using stored instructions. So the 5 components of any computer system are input, output, processor, memory, and storage. Another look at data, digital versus analog. Digital data, discrete values, like a light switch, 1 or 0, on or off. Analog data, more like a dimmer switch, where you have a continuous range of values and you can never get it exactly precise. So, how is data handled inside the computer? Well, it depends on the piece of hardware that you're talking about. For example, inside the CPU and RAM, data is represented by the flow of electricity using a series of microswitches known as transistors. In the on position, electricity flows through and it represents a 1. In the off position, electricity is not allowed to flow through the microswitch and it represents a 0. With magnetic storage devices like hard drives, floppy drives, and tape drives, the way we represent data is through magnetic polarity. The magnetic surface of the disk or tape is given a magnetic charge of either positive or negative to represent 1 or 0. Our optical storage devices, like the CD and DVD, use reflected light to represent 1s and 0s. A series of divots called pits and flat spaces called lands are used to either reflect the light from the laser or not reflect the light from the laser, therefore representing a 1 or a 0. Don't worry, you didn't bite off more than you can chew with this. Take a look at the binary digit, that's 1 bit. If you take 8 bits and put them together, that's 1 byte. Additional denominations include the kilobyte, the megabyte, the gigabyte, the terabyte, the petabyte, the exabyte, the zettabyte, and the yottabyte. Each of those is represented by the letter KB, MB, GB, TB, PB, EB, ZB, and YB, respectively. In each case, both letters are capitalized. If you have a capital M and a lowercase b, that's a megabit, not megabyte. And there's a big difference between the two. In fact, a megabyte is 8 times larger than a megabit. Do you know why? If not, ask in muddy points. The approximation of a kilobyte is 1,000 bytes, a megabyte, 1,000,000 bytes, a gigabyte, 1,000,000,000 bytes, a terabyte, 1,000,000,000,000 bytes, and you get the idea. Ever thought about becoming a computer programmer? Well, here's some information about the difference between source code and object code. Source code is the human-readable, editable version of the computer program, and it is stored as ASCII text. And while ASCII source code is easy for humans to read and edit, the computer doesn't understand it at all, and source code must be converted into object code before the computer can do anything with it. For this reason, computer programmers use a utility called a compiler to convert their source code into object code. Compilers are designed to convert a specific programming language into the instructions for a specific CPU. These instructions are stored as 1s and 0s in an executable file that a human can run or execute without access to the source code. Now let's take a brief look inside the CPU, the Central Processing Unit. A CPU has three primary components: a control unit, an arithmetic logic unit, and a series of registers. These three components together comprise what we call a core. A single core has a control unit, an ALU, and its own set of registers. If that core resides on a single block of silicon known as a die, then we call it a single core processor. However, if that die contains more than one core, then we're dealing with a multi-core processor. The example on the screen shows two cores on one die. That's a dual core, baby. Let's take a ride on the CPU train. One cycle is comprised of two stages. The first stage, going through the control unit, is called the instruction cycle. The second stage, going back up through the arithmetic logic unit, is called the execution cycle. Let's do an instruction cycle. The control unit fetches or retrieves an instruction from main memory into the CPU register called the instruction register. Next, the control unit increments the instruction pointer register to show the location of the next instruction in main memory. Then, the control unit breaks down or decodes the instruction to the corresponding CPU's own instruction set. Once the decode is complete, the control unit signals the ALU to take over. We're finished with this part of our journey, so take it away, ALU. The ALU accesses the operation code of the instruction in the instruction register to determine what function to perform and obtain the input data for that instruction. Next, the ALU executes the instruction. After execution, the results of the instruction are stored in the registers or returned to the control unit to be written into memory. And the last step along the execution cycle, the ALU generates a signal to alert the control unit to begin another fetch. And you guessed it, the entire cycle starts over. Down through the control unit for the instruction cycle, back up through the arithmetic logic unit for the execution cycle. Round and round and round she goes. Where she stops, nobody knows.